Okay, so what did we learn last unit when we did a comparison table? I need all of you boys just to be with me right now. Okay, so you don't have to watch the video at home. And you can go back to that after. Okay. What did we learn in the first unit when we did a comparison table with our properties? We learned a lot, didn't we? When we can compare and contrast the similarities and differences, our brain can like tag it to our memory a lot easier. Whereas if we're just trying to remember one-off things, they're much harder. Okay, so having a table like this constructed already, which I did yesterday for you, so you should absolutely have gone, ooh, that looks important, ooh, that looks like an easy way to learn all the information. Yes, I wrote it down. And then you can just continue on today, as opposed to this being your first crack at the wheel, which I've already rolled twice, if not 3 times. Okay, so Boyle's, what did he hold constant?
Temperature.
Pardon?
Temperature.
Temperature. And he looked at the relationship between pressure and volume, and he found that they were inversely proportional, and so we draw it like this. And inversely proportional means as I increase pressure, the relationship is increase pressure, I decrease volume. That's what inversely proportional means. Increase, decrease. In fact, it also means double, half, or divide by 2, right? Times that by 3, divide that by 3. So, decrease in volume by an exact amount. 2 times the pressure will equal half the volume. And the formula that we came up with, you use this and you rearrange it to keep P and the V on the same sides. Multiply V, and you get P1 times V1 equals a constant. So we can have that equal the second situation for that balloon. So if I take a balloon and it has a pressure and a volume, and I keep the temperature constant, but I squish the volume in half, my pressure will double. Okay? Same balloon, same temperature, just different situation. And the graph looked like this. Oh, I've now put it in different order. Shouldn't matter, you already have it written down from yesterday.
Yeah.
The graph looks like this. Pressure and volume gave us a curve, so we then took pressure and inverse volume, inverse volume, and I get a straight line. And then we're thinking, oh, the curve went the other way, didn't it? Sorry. And so that's linear relationship tells me, like the fact that I had to take the inverse to get a linear relationship, went the other way? Thank you. Tells me that I have an inverse relationship there too. Okay, so the fact that I need to take the inverse to get a linear line tells me the relationship is inversely proportional. Comparing that to Charles, well, what did Charles hold constant? Pressure. And what did he find the relationship to be? Wait. I just asked you if what Charles found constant, right?
Yeah.
When you're doing that, are you just trying to pluck it out of the sky? Are you visualizing the graph and knowing what the P1, P2 meant on your graph? Are you visualizing what you've labeled your axes to know that it's the other one? That was... Do you see how all these different places that you can draw from your memory as opposed to just plucking it out of the sky? Okay? So also in your graph, you found that the relationship, what were your axes made up of? In the graph you're just doing right now, you guys at the back of the graph you just handed in. They were temperature and volume on your axes. So that must be what the relationship was, and the other thing must be constant. Did you have to do 2 graphs? Did you have to make it inversely, or could you just do the one? Just the one. So what does that tell you about the relationship? They're not inversely proportional, but rather they are directly proportional. And so that means that if I increase increase temperature, the balloon will expand. Increase the volume. Increase temperature, increase the volume. Does that make sense? Yes? Okay. And so if I am writing this as a formula and I try to bring V over to the other side, T divided by V is what I ended up... No. V divided by T is what I end up with. I could have ended up with the other way, but they chose not to. And that will equal V2 divided by T2. And we have to remember to change our temperature into Kelvin. And the graph on these all looked linear right away, the temperature and the volume. As I increase volume, I increase the temperature. You can see that linear relationship there. Makes sense? Okay, so I'm going to compare this, and you're not going to do a graph for boils, because we should be able to deduce all the information that we need. So boils, I didn't mean boils, and I spelled it wrong again. I meant Gay-Lussac. L-U-S-S-I-C. Lussac. Okay, so in your packages, there's a teeny tiny little paragraph. Lussac, apparently. Gosh, that's an unfortunate name. I believe that they were two. That's the first time I noticed that, and I've taught this for many years. There is, I'm glad somebody else has the same sense of humor as me. There is a tiny paragraph about it in your books, but that's it, because we can kind of already guess everything that we would have to write down. So, what did they hold constant? Volume. Because there are three things. So if he did temperature and he did pressure, they must have done volume. And what relationship do you think they came up with?
Pressure, temperature.
A relationship between pressure and temperature. And now let's just think. If I have to hold the volume of my balloon constant, or my cylinder constant, and I'm going to increase the temperature, turn it up. What happens to those particles? They move faster. So what happens to the pressure? It increases. So an increase in pressure should an increase in temperature. Those are related. Those are directly proportional. And in a minute, I'm going to have you walk around the room and demonstrate each of these three things, just to get you moving today. Okay, so if I increase and increase, and the relationship then, bring the T over to the other side, and you get, you get P1 divided by T1 equals P2 divided by T2, and if you did do the graph, what would you find about the relationship? Right away it would be linear, because they're directly proportional. Happy? So I want to explain this pressure and temperature increase. So what is pressure? Why does something have a pressure? Why does the balloon stay inflated?
It's like the force of particles hitting the container.
Good, the force of the particles hitting the outsides of the container. So,
Cloud change.
if I increase the temperature, what am I doing to the particles? They move faster. Okay, they move faster. Everybody okay with that? If they move faster, they hit the sides with more force. Hit sides of container with more force. Okay? And if they're hitting the sides of the container with more force, and I have to keep the volume the same, it would be lovely if it could expand, right? But it can't expand, so therefore my pressure must increase. Make sense? So if these particles are just bumping against the wall and going, that's not much force. That's not much pressure. If I have a full steam ahead interaction with the sides of the container, then I have more force. The volume must stay the same, so therefore the pressure increases on that wall, or balloon, or container, or whatever. Okay? The end, really, about those three laws. So somebody said, well, you know what? Like, what's the real probability of that wall not expanding? In fact, it did for a second, a millisecond, a tiny vibration. Not much, it was just my elbow. But a tiny vibration of that wall expanded. That balloon, if I increase the temperature, what's the probability of the volume staying constant? None. Right? It's going to expand, so I'm playing with all three variables at the same time. As soon as I turn up the temperature, it's going to increase the pressure a little bit and increase the volume. Every time you do something in real life, all three things change. So these experiments are great for experiments, but not so great for real life and reality. So somebody looked at all three of these things and said, hey, you know what? Let's combine them. And they came up with the combined gas law. Now the combined gas law, I'm going to look at these formulas. Here's one formula, here's another formula, here's another formula. And I'm going to, it'd be great if this was clip art, I'm going to take out that from the board and I'm going to superimpose it on this. So I'm starting with P1V1 equals P2V2, that was the first one. The next one, Charles says that the V1 divided by T1 equals V2 divided by T2. Do you see that? And then superimposing Gay-Lussac's, well, it's already there. P1 over T1 equals P2 over T2. So combining all three laws, I end up with this one law, a combined gas law, which means that I could change three things and have three things then be affected. Does that make sense? But I couldn't do the experiment like that because we all know we have to control one thing and only look at two things in an experiment. So they had to go through all three of these experiments before they could come up with a combined gas law. Now the great thing is, we've already kind of talked about how memorizing these bits we should kind of be able to visualize in our head. Right? What was the first graph I did? Oh, that was Boyle's. Oh yeah, we had to do those two graphs. One was loopy-loop and the other was straight. That must mean they're inversely proportional. There's my answer to that. Boyle's law has to do with pressure and volume because it was the first sheet I did. Whatever. Because it was the first graph I did, and those are my axes that were labeled. So visualizing the order that you did these in should help you visualize what the graph looked like, what they're called, who did the law. Does that make sense? But the formulas, we only have to memorize this one. This one formula. It's not four formulas, it's one formula. Because if I have a balloon, it has a pressure, a volume, and a consistent temperature. And I keep that temperature the same. And I change the volume, what's the new pressure? See that? And I now have the right formula. Boys, go back to putting our T's in place. And now I'm going to hold the pressure constant. So I rub out my pressure, and now I have what you're working on, just finished working on. Do you see that? So you actually only have to memorize the combined gas law, and then you can erase whichever variable is held constant, or you could use all three if the question's about changing all three things. Does that make sense? Yeah. Okay. So for those of you that are ready, we're gonna do a little interactive thing. But in order to practice the combined gas law on the very next page, you can do questions 1 to 6, where it says gas laws, assorted problems. Okay, so that's what we're going to do for the last 20 minutes of class. Okay, but for now, stand up. Tuck your